When we draw a Lewis structure for a molecule or ion, we need to be able to decide where we're going to say the charges are going to lie on it. I'll point out we can also have charges within a neutral molecule. It's just that those total charges have to add up to be 0. So even neutral molecules will sometimes have full-size charges within it, at least when we do our bookkeeping method here. Now I'll also say that there's going to be a different bookkeeping method we can use for charges that we'll talk about later in the course called oxidation number. You've run across that term when we talked about transition metals and their charges. We were referring to those charges like iron 2 plus or iron 3 plus as being oxidation numbers, iron 2 and iron 3. Well, it's a different bookkeeping method, and we will talk about it in other videos. But here we're going to focus on formal charge alone. So this is just going to be one way of deciding where we think bonding electrons are hanging out. Now, in this assumption, we're going to assume that the electrons are completely evenly shared in the bond. This is a surprising nuance that a lot of books totally omit, and I really want us to understand it. I mentioned there's these two bookkeeping methods. This one is going to assume that shared electrons are completely evenly shared. The other, oxidation number, is going to assume that they are completely ionic, not shared at all. And it's a winner-takes-all sort of scenario where the most electronegative atom gets the electrons every time. We're not going to get there later on, but here I want to focus on formal charge, which is the assumption that we have 100% covalent bonds and totally even sharing. Now, with that in mind, it makes a lot more sense what we're going to see in the equation you see in most books. And that's where they tell you to take, for formal charge, take your valence number of electrons, or better to say probably your octet number of electrons counting towards your octet, minus a combination of your unshared electrons and half of your shared electrons. Okay, that's some fun memorization, right? But what does it mean? What it's telling you is that we're going to start out with the number of electrons that the atom brought to the party. Then we're going to see how many it has once it starts sharing. So this is how many electrons it brought with it. Now we're going to count up how many it's not sharing, and then half of each of the ones that it is sharing. In other words, half the shared electrons, 100% covalent. It still owns half of all bonding electrons. That's the idea of formal charge. Now let's see an example of that at play. Let's do the formal charges for the structure that you drew for CO3 double minus. If you didn't do that one previously, go ahead and pause and draw the Lewis structure for it. Decide on one of the resonance structures to do, and then go ahead and assign formal charges. Pause and give that a try. Okay, so we end up having C, O, O, O. I'm just going to do this one quickly. Let's see, so we're going to end up having 3 pairs on that one, 3 pairs on that one, and 2 pairs on this one because one of them has been pulled in to make the double bond right there. Let me just clean that up a little bit. There we are. So this is going to be mine. You may have the double bond over here or over here. So what we're going to do for the formal charge is we're going to consider each atom type that we have in there. We have a double bonded oxygen, we have a single bonded oxygen, and we have our carbon. We can still do these separately. Just we're going to get the same answer, so I'll save us a step is all. So let's start out with this one. This oxygen brought 6 electrons to the party. We know that because it's in column number 6 on the periodic table. So we started with 6 electrons. Now we're going to count up all of its non-shared electrons. So 2, 4 electrons. Let's see, so we're going to subtract 4 plus half of the shared electrons. Notice in this case we have a total of 4 electrons being shared. Half of those are going to be these 2. So we're going to have 6 minus 6 equals 0. So we'll have 0 for its formal charge. I'm just going to go ahead and write it in like this. Oh, that looks like a 6. There we go, a 0. Now let's go ahead and do the same thing for our central carbon. For the central carbon, it brought 4 electrons. it's going to have access to all of its unshared electrons, which happens to be 0, and then half of its shared electrons, 1, 2, 3, 4, gives me a total of 4. 4 minus 4 equals 0. Once again, we have a formal charge of 0, which seems entirely uninteresting so far. But check it out what's going to happen on this one. So, oxygen brought 6 electrons to the party. There we are. It has 6 unshared pairs. I'm sorry, 3 unshared pairs for a total of 6 electrons. It's going to have half of its bonding electrons, 1. And so that's going to be 6 minus 7 equals a -1 charge. Now I'm going to show you a different way to do it that's the exact same thing, but instead of doing it like a math problem, we're just going to talk through it, which is how you're going to be able to do it quickly while you're drawing the thing in the first place. Oxygen brought 6 electrons with it. It's got 2, 4, 6. 1 here, 7. 6 minus 7, this will be a -1 charge. You really want to be able to go through formal charge that quickly whenever you're drawing these things. Now notice, we've got ourselves a structure that has the -2 charge distributed at 2 different electrons. We also know that there's going to be resonance structures. So I'll point out that we're going to have a double bond that can shift over here or over here. That means all of these bonds are going to be at a bond order of 1.3. So bond order 1.3, or 1 1/3 is what I'm writing there, for any of these. Why? I'm glad you asked. Single bond, single bond, single bond. We have one additional bond, the double bond, right? That single bond can be divided into 3 different places. When it is, you have one bond plus 1/3 of a bond, 1.3. One bond plus 1/3 of a bond, 1.3. And so if we wanted to do it like that, we'd actually have to draw our dotted lines. But I really want to point this one out. If I actually draw this as a resonance structure like this, I probably don't want to be drawing in my partial charges because they're not going to mean much anymore. I'd actually have to start having fractional charges. If I have -2 and it's going to be distributed in 3 different places, that's going to be a -2/3, which is going to start looking really funny to us and isn't going to make much physical sense. So I don't recommend doing that.